What up, family? It is the 2nd of September. It is a Friday, because I know what day it is every day. And we are here to discuss and review some Big O notation stuff. So, here's the first thing. I have technically it's like 6 pages, but I have 2 documents that I want to go over with you guys, and then we'll see what happens from there. So first off, this is the Know Thy Complexities sheet from this BigOCheatSheet.com. It's I use this in the hash table video. This is just a graph showing different complexities stacked up against each other. Let's start here. So with arrays, arrays have an O1 average and worst case for access. If you think about it, arrays are what's the word? Arrays are defined by elements. There's a word for it. Indexed. Arrays are indexed, right? So if you want to access array element 7, you just put the array and then brackets and 7 inside of the brackets, and you'd have access to that array, that element in the array. Moving on, search, insertion, deletion are all O of n in the case of an array, because if you think about it, an array has n terms, right? So if you want to search through those terms, there's no in the terms of just an array, there's no fancy search method, or you're not sorting anything, so you don't have to worry about it. But search of just a vanilla array, you would just have to go iterate over the array and then find the elements until you get to the element that you're looking for. But then you get into you have to consider values and then indexing and all this other stuff. And then space complexity. If you think about it, wow, I've said that a lot. Space complexity, if you I want to say it again. So space complexity for everything except the skip list, which I'm not sure of yet, are all O(n), because you have n amount of elements, right? So that should make sense. And then these obviously change because these are sorting algorithms. But everything, essentially, except this, skip list, is O of n. And moving on, if you go to a stack and a queue and a singly linked list and a doubly linked list, these all are characterized by this exactly the same access, search, insertion, and deletion for average and worst case. Obviously, all of these are all O(n) still for space complexity. For stack access, you'd have to go through n elements, right, to get to access whichever element that you're trying to get to. See, the thing is about stacks, generally, I guess fundamentally, stacks aren't defined by indexing, because they're just, essentially, you're just plopping information on top of each other until you have a stack, I guess, essentially. We will go on to search of all of these data structures, the stack, the queue, singly linked, and the doubly linked list. They're all the same average and worst cases of each of its respective category. Because if you think, if you want to search in a, let's say, singly linked list, you have to go through n elements to find the element that you're trying to find. Because there's no, yeah, that makes sense. Because there's no indexing for any of these, generally, I guess, as a fundamental rule of each of these data structures. And then with insertion and deletion, pretty much all of these have a head node, or in the doubly linked list, you have a head and a tail. So I guess the difference between doubly linked lists and any of the other 3, the stack, the queue, and the singly linked list, they all pretty much just put attach data to wherever the beginner node is, or the in the doubly linked list, the head or the tail. Yeah, the head or the tail of the doubly linked list. So insertion and deletion are constant, because when you insert something, you just add it on to wherever the head node is, or the tail node is, in the doubly linked list sense. And when you delete something, you already have the node that you're trying to delete. Generally, you don't just go swinging into the data structure randomly deleting stuff, right? So that's constant time as well. and it's consistent throughout the average and worst case. So then, moving on, we're going to skip to, we're probably only talk about the hash table, which we just did, which, with access, I'm not entirely sure why hash table doesn't have access. If you think, let's think, a hash table not having an access, big O, you don't need access, because access is just search, though. In the hash table sense. Because if you think about it, a hash table doesn't really need access because access is implied through search. Because if you have a key value combination and you can't generically pick out a key and value combination assuming the data isn't set yet, I guess, if that makes sense. There's no reason for having access. And even if there was an access, you could kind of associate it with search, because if you wanted to access whatever's at key 6, you would just put in map or hash table.get and then 6, and then you would have access to access and search of constant time. So I believe that's why there's no access section or access big O. So then regarding search, insertion, and deletion for the average case, they're all constant time, if you can, right here, if you follow, right here. They're all constant because, look up, hash tables fundamentally are defined by a key and value combination, right? So each key, assuming it's implemented correctly or appropriately, each key should hash to the corresponding value, right? There should be no guessing, and collisions shouldn't be a problem, whatever. So assuming that's implemented correctly, everything is associated one-to-one, in a sense, if you want to think of it in math terms, I guess. Yeah, so that's why hash table is constant time, O of 1, because you plop in a key value, a key, and then you get back a value, and that's why it's all constant time for the average case. And the worst case for hash tables are for search, insertion, and deletion. They're all ON, because worst case, this is assuming that the hash table is implemented incorrectly or just poorly. Because if you have a hash table, if it's implemented poorly, and we'll just assume that everything hashes to the same bucket, then you have to iterate through the bucket that you have already, and iterate through those elements of the bucket that are all already preoccupying the bucket to find your value. And in a sense, you're just working with a glorified array. So we're going to move on, because I'm not going to touch on these, because these would take a while to explain. Also, I don't know maybe 50% of them, which is not good. So I need to definitely touch up on my big O. Yep, need to touch up on my big O. Then there's this awesome little explanation of how big O is explained and how it's calculated, I guess. So we're going to run through an example, and then we're going to pretty much just run through the examples one at a time. So for example 1, prove that running time t of n is equal to n cubed plus 20n plus 1 is O of n cubed. So my issue with big O is when I was in my Calculus 2 class, we learned about relative growth, I guess. I don't know, I forget the formal term for it, but pretty much you'd have you'd have two functions, and it would say which one grows faster and why, and then you have to put them on top of each other according to this, some principles, and then you calculate it out and see which one won. But if you think about this in terms of big O and computer science kind of stuff, what I've read just on my own about big O is with big O and having a an equation like this one right here, the n cubed plus 20n plus 1, if you were to plug in any number, let's start with 1 for n. You'd have 1 plus 20 plus 1, which is 22. So that's not a really big change, you know? So let's go to 10. So if you had 10 to the third, it'd be 1,000 plus, 10, 100,000, yep, because I'm bad at math. 1,000 plus 200 plus 1, so it's 1201, which is much bigger than 1, right? And you could say that they are increasing by an order of n cubed. Essentially, as these are limits, so as n approaches infinity, the bigger the thing gets, the bigger the amount gets, right? So let's just run through the proof, I guess. We'll skip down to the proof. So by the big O definition, T of n is O of n cubed if T of n is less than or equal to C times n to the third for some n that are greater than or equal to an n naught. Let us check this condition. If n cubed plus 20n plus 1 is less than or equal to C times the n cubed, then 1 plus 20 over n squared plus 1 over n cubed is less than or equal to C. Oh. Wow, okay, that's great. Okay. So you're just doing algebra. So you have this, assuming this, and this is the equation, assuming this equation, T of n, right? T of n is less than or equal to this. Then you just divide over the n cubed. So n cubed would go under all three of these, I want to say elements, that's all of these numbers. So n cubed over n cubed is 1, and 20n over n cubed is 20 over n squared, and 1 over n cubed is 1 over n cubed. And then you're just stuck with less than or equal to C. So therefore, the big O condition holds for n is greater than or equal to n naught is equal to 1, and C is greater than or equal to 22. So you're just plugging in 1, you're just plugging in 1 for this side of the equation to find C. And then you have your, pretty much, so 1 plus 20 over 1, which is 20, plus 1 is 1 over 1, which is 1. So 1 plus 20 plus 1 is 22, and then you'd have 22 is less than or equal to C. And then you just flip around the equation, and you have C is greater than or equal to 22. Larger values of n naught result in smaller factors of C. For example, for n naught is equal to 0, C is greater than, n naught is equal to 10, C is greater than or equal to 1.201, and so on. But in any case, the above statement is valid. N naught is equal to 0. N naught is equal to 10. So if you have 10, 100, you're just placing 10 for n, and then solving for C, as defined here. So if you were to put 10, it'd be 1 plus 20 over 100, and then plus 1/1000th. So then you'd have 1.201, and so on. But in any case, the above statement is valid. Okay, so moving on, prove the running time T of n is equal to n cubed plus 20n plus 1 is not O of n squared. So essentially this is the same thing up here, right? So we'd prove by a big O definition, the definition for some n, let us check this condition if this is less than or equal to C times O n squared. Oh, cool. Okay. Therefore, the big O condition cannot hold. The left side of the ladder inequality is growing infinitely, so that there is no such. Oh, yeah. Okay. So this is, it's just glorified growth, like comparisons, I guess. So if you want to prove that n of something, let's get a Word doc out. Okay, so we're going to move on to proof 2. So let's put this to this. So proof 2 says, prove that T of n is equal to n cubed plus 20n plus 1 is not O of n squared. So prove that that the equation is equal to the equation, the time of the equation, is not O of n squared. So if you just look at this, if you just were to look at the example, you should be able to tell that n cubed is going to be the biggest growing factor of all of these, because if I had just n, because if we were to remove all the constants and just think of this in terms of n's, you'd be left with n cubed plus n to the 0th. So then you'd have, let's say you plugged in 2, and you'd have 2 to the 3rd plus 2 plus 1. 2 to the 3rd is 8, and then it's just 2, so 8 is growing faster than n. So if you think about it, n cubed is always going to be greater than n, right? So that's just something to point out. And then regarding the question, prove that running time is this, is not. So then we have to plug it into our big O. So t of n is O of n squared if t of n is less than or equal to c times n squared. So for some n, for n, some n equal to n naught. Okay. So if we plug in, so if you see here, t of n is here, right? And t of n is equal to this. So let's plug in t of n for this. So n cubed plus 20n plus 1 is less than or equal to c times n squared. So now that we have our example, our proof, I guess it would be, that's what they call it, or just a check, I guess, yeah. So then you, what do you do algebraically for something like this? We do this one. So you would divide by n squared, right? So then you'd have n cubed over n squared plus 20n over n squared plus 1 over n squared is less than or equal to c. And that's what you have here, right? So it's saying, check the condition, do this, and then you have this. So this right here, n plus 20 over n plus 1 over n squared was less than or equal to c. Then we can just, this is just a simplified version of this. So then this would be equal to n plus 20 over n plus 1 over n squared less than or equal to c. Therefore, the big O condition cannot hold. The left side of the ladder inequality is growing infinitely. So why would that be? Because there's an n, right? So let's say we take a constant, and we say the constant is 5. And we also plug in... Oh, okay. So is there any point at which c is... So it's a proof. You're disproving whatever the inequality is. So let's try to find a number of n that is less than, that is greater than 10. So let's say this is 10. So we're going to say n plus 1 over n squared is less than or equal to 10. So assuming c is equal to 10, we'll set n equal to 5. C will, constants will always stay constant. So let's just do a ridiculous number. Let's do 10,000. Yep. So if we were to plug in 10,000, we'd have 10,000 plus 2 over 1,000, or 1 over 500 plus 1 over 10,000 squared. So this is equal to 10. So you just think about this. If we were to just cut this out, is this statement true? Is 10,000 less than or equal to 10? No, it is not equal. It is not less than or equal to 10. So that proves that this equation, n squared, n cubed plus 20n plus 1 is not O of n squared. Okay, so let's move on. Prove that running time t of n is equal to this. We'll just go back to this because I'm pretty sure we can follow now. So prove that running time t of n is equal to n cubed plus 20n, whatever the equation is, O of n to the 4th. So proof this. So pretty much you're doing the same thing. You're setting the equation is less than or equal to c times, and then the challenging O, big O, for some, and this is just, okay. Let us check this condition. If this is this, then you get this, 1 over n plus 20 over this plus 1 over n to the 4th is less than or equal to c. Therefore, the big O condition holds for n is greater than or equal to n naught, and 1 is equal to 1, and c is less than or equal to, c is greater than or equal to 22. Large values of n reduce small factors, but in any case, the above statement is valid. Oh! Prove that running time of n cubed big O condition holds. That's weird. Okay. That's really weird. Prove that running time of this is O of n cubed, n to the 4th. It's just trying, oh, that's weird. Okay. So it's saying it's weird because this, the big O of this is n cubed. So, but this is n to the 4th, and it's saying that this is a valid statement. Assuming the conditions hold. Okay, that's a formality. So, therefore the big O condition holds, this and this is greater than 22. Oh, cute. Okay. Because we plug in 1 and they're all over n, there it's going to be 22. Because for some n are greater than or equal to n naught is equal to 1. If you just plug in n for 1, then you'd have 1 plus 20 plus 1, because 1 to any power is 1. So then you have the same thing as this one. C is greater than or equal to 22, and you just go through the actual of these, the rest of these. And you have large values respected n naught is equal to 10. It just adds a little decimal, because previously it was 1.201, right? 1.201 right here. And then because the powers on the bottom of the numbers of the numbers being divided by the powers of n distort the output, or distort the values by a factor of n, because it's n to the 4th. So I guess assuming the definition of what big O is, checking if you check the condition, this condition, it's valid, but it's not. I feel like it's valid, but it's not true, because if you think about it, if I say prove that running time t of n is equal to n cubed plus 20, the equation 20n plus 1 is O of n to the a millionth, then you're just having the same thing, except these are extraordinarily small. And it's still true. It's a valid statement. It's just to say that something is big O of n to the millionth. It just doesn't. I don't know. It doesn't sound correct. I mean, it says that it's valid, which is fair, but I guess I will have to look more into this. Interesting. Okay. So big omega. Prove that running time t of n is n cubed plus 20n is omega of n squared. By the big omega definition, t of n is omega n squared if to the same thing for something is greater than or equal to. Okay, so we're checking the big O. Oh, that's funny. Okay, so big O versus big omega. You're just flipping this what is this, inequality sign symbol? Yeah. So you see here, this is greater than or equal to right here, and then up here it's less than or equal to, right? So greater than or equal to, and then whatever's inside the parentheses of the big omega, and then you solve for c. Left side inequality and minimum is this, where n is equal to the root of 20. Therefore, the big omega condition holds for n is greater than or equal to n naught equal 5, and c is less than or equal to 9. Larger values of n naught result in larger factors c. For example, this, plug in 10, c is less than or equal to 12.01, but in any case, the above statement is valid. The big omega is n squared. So what happens when you change the inequality sign regarding a formula, regarding a comparison? So for some, okay, if n cubed plus 20n, so if you divide this out, you get this, and this is where it's stuck. So n plus 20 over n is greater than or equal to c. Left side of the inequality has a minimum value of this for n is equal to the root. If you had root 20 plus 20 over root 20, why is that? So 4.47, therefore the big O holds for n is greater than or equal to n naught equal to 5, and c is less than or equal to 9. Oh! Okay. Yeah, cool. Okay, that's neat. So assuming that you're using big omega, you plug in t of n is greater than or equal to c times n squared, because this is what you're solving for, right? The n squared. And then when you solve for this, assuming that as n changes, the statement stays true just like all the other ones. Wow, this took me a while to understand. Assuming that the inequality, assuming that stays true, this is a valid statement. Okay. Wow, we learned stuff today. Okay, so larger values of n naught result in larger vectors of c. For example, this holds true for c is less than or equal to, and then the c of whatever the plugged in of n naught for 10, 10 for n naught, I guess. But in any case, the above statement is valid. Okay, so think about it. So this is how I'm going to practice. So let's see. Let's try something with a big omega, because that was pretty interesting. So let's say t of n is equal to n cubed plus, oh, not that, n to the 7th plus 67, that number, to the 5th, is big omega of n, so greater than, so you want it to be, let's just say 8th, big omega of n to the 8th. I should probably use Vim because I'm much faster with that, but too late for that. So, okay, so let's say we have this. Oh, you know what? We're gonna do some Vim stuff. Copy that, discard that. Okay. So we're not going to do that. So T of n is equal to this equation is equal to big omega of n. So we have to prove that this is such. So what we would do is we plug in the equation. 64 n to the 5th is greater than or equal to c times n to the 8th. Right, because this is what is said here, because that's what we're comparing it to. I know for a fact that this is going to be false. That's what I'm gonna say for now. So n7 plus 64 n to the 5th. Wow. C times n to the 8th. Sorry about that. So then we'd have n to the 7th over n to the 8th plus 64n to the 5th over n to the 8th. Why can't I hit the caret today? That's weird. We would be left with 1 over n plus a constant 1 over n to the 3rd is greater than or equal to c. Okay, so now if we were to plug in 1 for this equation to find our c, because, where is it? This, oh not, so this, this right here. So, if we, not that, this. If we set n is greater than or equal to n not equal to 1, then we find out whatever the c, we're comparing c to. So if we plug in 1, so let's let n equal 1 for the processed solving for c. So n equal 1, then it would be 1 over 1 plus 65, 1 over 1 to the 3rd is greater than or equal to c. So then we have 1 plus 65 is greater than or equal to c, which we have 66 is greater than or equal to c. So then we have to make sure that this is true, right? So what did they do first? They swapped it, swiggity swapped it. Where is it? C is less than or equal to, right? Because it's swapped 66. So let's find this. So we need to find a value that disproves that this is that C is and not for 10, but in any case the above statement is valid. Oh, sick. Okay. So they're holding a move-in video contest for move-in day, which is cute. I don't know if we'll do anything, but we'll see. So, comparing for big omega, we have C, right, C is less than or equal to, and C is less than or equal to large values of n naught result in larger factors for this, but in any case, so let's plug in 10 for n naught, which is technically just n in this sense, I guess. It'll be 10 plus 65 of 1 to the 10 to the 3rd is greater than or equal to 66. So then we have 1 over 10 plus 65 of 1 over that many is greater than or equal to 66. So then this is false. Yes! We're learning stuff. Okay. So because it's big omega and not big O, if you add 65 over 1,000 plus 1 over 10 is greater than or equal to 66. So, what have we learned? This is false because 65 1,000ths plus a tenth is nowhere near a 66. And because this is false, this means that the statement that that this equation is big omega of n to the 8th is false, because big omega is you're swapping the inequality. So if you think about it, when it comes to big O, you want your big O to be okay, I got it. So with big O and big omega, with your big O, you need your O, your T of n, T of n, okay, so whatever's in your T of n, the highest, so the degree of T of n has to be, if you want to be true, so if big O equal to true, you want your no, that's not correct. If you want this to be true, if you want big O to be true, you need you need the degree t of n. You need the degree of your equation to be less than. It has to be or equal to. Has to be something than the big O of whatever your equation, whatever the equation is. So you want your degree of the equation to be, for it to be true, you want it to be greater than or equal to the big O of your n, for it to be valid. For big O, okay, so big O to be valid. Okay. Consistency. Those will be two different variables, so this is kind of awkward. But what happened? Okay. So that makes sense, right? Because for the big O, if you remember here, for this, okay, so big O, what we're checking against is n cubed, which is equal to the degree of t of n, right? So that solves this case. So that's true. Big O is valid. And see in the statement here, statement's valid. So then with big O is less than the t of n, this is not valid. The condition cannot hold because it's false. So that's also true because this is the n, the degree of your challenging n, big O, I guess, is less than the degree of your t of n, the equation that you're using. So now for big omega, with big omega you just switch the inequality in the t of n equation right here. So when you switch that, it would be if degree of t of n is less than, would it be or equal to? I guess we'll have to find out. Big O of x of the whatever challenging. Oh right, we're not saving this. So big O is equal to invalid. No, we're not saving this. Okay. So this makes sense because, wait, we have to check. So wait, if it's, no, this would be true. This would be valid because if the big omega, if the big omega is less than, right? Because so the big omega of this is less than or equal, is less than, just in this case, less than this, then it's valid, right? Because it's valid. Because you're swapping the inequality. It's, I don't know if this is making sense, but when you swap the inequality, you're changing which way the n has to go to make it valid or invalid. I hope that follows. I hope that makes sense to you, because it makes sense to me. That doesn't really justify my thinking, but so moving on. For big omega to be valid, you want your whatever the challenging n is to be less than, or would it be or equal to? Because if you did or equals to, with big omega, if it's, so we found out with n is greater than, when the challenging n is greater than the t of n's degree, we found out that this is false. So that means if the degree of the t of n of the equation is less than, oh no, these are, wait. Why are these backwards? Wait, degree of t of n is greater than equal to, is greater than or equal to this. Oh, I think these are backwards. So think about it. The big O that you're challenging with is this. Okay? So with big O, if this number, in this case, let's say at example number 3, if this number is greater than or equal to the degree of the t of n, this is valid. So this is true. This makes sense. So then with big omega, it's swapped in the sense that if big O, if the challenge big O is less than or equal to the degree of T of n, we know that it is, we know that it is valid. So then, okay, so we need to prove that it's equal. So we know that if it's less than, it's valid, and if it's greater than, it is invalid. So if it's equal to, let's just do a quick run through in our head. So T of n, well, not in our head, on the screen, because those words totally matched up, is big omega of n squared. I mean of n cubed. So we set T of n, which is n cubed plus 20n, is greater than or equal to c times n to the third. So if we did this, we would end up, if we divide by n cubed to both sides, we'd have 1 plus 20 over n squared is greater than or equal to c. So if we plug in 1 for the n of the original problem, we will find out, so if we set n equal 1, then we'd have 1 plus 20 over 1 greater than or equal to c. So 21 is greater than or equal to c. So then if you plugged in 10, we'd have 1 plus 20 over 100, which is that, and then 2 over 10, which is 1 over 5. C. So we'd have 1 and a fifth greater than or equal to c. So what does that tell us? O is valid. So as n gets bigger with big omega, because it's opposite, you want it to be decreasing to be valid, right? Because that would make, oh, not decreasing. No, yeah, decreasing. That would make it true. Because in the event, like the one we had above, you want c to be less than or equal to this. So if we set this 21 greater than or equal to c, let's say this is 21, is 1 and a fifth greater than or equal to 21? It's not. So that means larger values of n naught results in larger factors. So is this getting bigger? No, it's not. So this is false. Because what in case the above statement is valid, because you want your challenging n of the big omega to be less than or equal to the degree of the T of n, less than. So larger values of n when it's equal, because this is n cubed and this is n cubed, is decreasing, which is smaller, which means for larger values of n naught, the values will be smaller, which is which makes this valid. So that means that this is also true. So the equal statement is valid. So if the big, wow, that's confusing. If the big O, if the degree of T of n, if the big O of the n that you're checking is greater than or equal to the degree of the equation that you're checking, the big O statement is valid. And then with this, the same thing, you want to be less than or equal to. Okay. Wow, we learned stuff today, guys. That's cool. We're not saving this. Sorry, muscle memory and stuff. Alright, well that is today's words video, and I think tomorrow, it's Saturday. I don't know what I'm doing tomorrow. We'll see about tomorrow. But until then, going to enjoy this wonderful jasmine tea that doesn't, it's still, I don't know, it doesn't brew very strongly. It's green tea in a red cup, so Merry Christmas. But I guess for now, happy Halloween. It is pre-October. I will see you hopefully tomorrow.